Hi everyone, this is Wang from TikTok Singapore. I joined TikTok a few months ago. Before that, I was at National University of Singapore. So the works to be presented today were done when I was at National University of Singapore. I'm going to review recent works, including our own works towards making an easy-to-use AI platform. We have seen massive adoption of AI and machine learning in various domains before the deep learning era. Traditional machine learning models like decision trees, SVM, were the backbone models for natural language processing, computer vision, and audio applications. Over the last decade, machine learning, especially deep learning, has attracted a lot of interest and funds due to the outstanding performance of image processing, object detection, machine translation, so on and so forth. We have thus witnessed the fast and massive adoption of AI and machine learning in these domains. However, the adoption of AI in some domains is actually slow. Let's take the database system as one example. The right figure shows the number of papers on arXiv containing none in the title, so from the database field. Actually, before 2017, there were few papers using machine learning, especially deep learning, for database systems. There are some papers using database techniques for machine learning. So you can see there are some few papers there. In 2016, we wrote a paper to discuss the challenges and opportunities of using deep learning for database systems and using database techniques for machine learning systems. We found that deep learning could be a good fit for query plan optimization and sentence to SQL query translation. Since 2017, we can see more and more papers applying machine learning techniques for database systems have been published, including the query plan optimization, sentence to SQL translation, learned index, cardinality estimation, SQL injection detection, and others. Actually, the best paper of this year's SIGMOD conference is given to a paper working on this direction. Compared with natural language processing and computer vision domains, the adoption of machine learning in database is actually much slower. We also tried to apply machine learning and deep learning for healthcare, security, and fintech applications. Personally, I think machine learning has huge potential in these domains, but currently the adoption is also progressing slowly. I think there are at least two challenges. First, to develop a successful application, the developers should have a good understanding of the application, the data, and the machine learning model. Which model to use for my application and data, and which data attributes should be used as the input to the model. The decisions directly affect the model's performance, including the accuracy, the precision, and recall. To resolve this issue, we have to educate the domain experts with machine learning knowledge and educate the machine learning experts with domain knowledge. This is because for non-traditional domains, like in the database systems, the machine learning experts may not be familiar with the application data, and the domain experts may not be familiar with the models. Today, I'm going to focus on the second challenge. So that is about the tools and the platforms to make it easy to use machine learning and AI techniques. The life cycle of a machine learning model based application has multiple stages, including data preparation, model construction, training, and serving. Typically, we have to train multiple versions of a model to tune the performance. And some complex applications will use multiple different models and put them together into a pipeline, as shown here. And in a large team, there could be multiple developers sharing the same GPU resources and the datasets. So it is necessary to manage the hardware resources, the model, the data and the training jobs in a platform. Therefore, the second challenge is providing an easy-to-use platform that integrates various tools to reduce the engineering cost for fast production. So this is sometimes referred to as ML Ops. Next, in the rest of this talk, I will review some popular algorithms and our own works towards an easy-to-use AI platform from the data preparation, model construction, training and serving, and the job management perspectives. After that, I will briefly compare some existing platforms, including the open source platforms and the cloud platforms. First, let's talk about data preparation. There are two metrics, at least two metrics that are important in the data preparation steps. They are size and quality. So here is a figure drawn by Andrew Ng. He did one experiment to study the effect of data quality, data size, and the data quality. We can see that when we increase the size of the dataset here by using more and more training examples, the accuracy can be improved. And if we compare two sets of data, one is the noisy data and another one is the clean data. So we can see that clean data has a higher accuracy than the noisy data. So it means we can improve either the size or the quality to improve the model's performance. Yeah, so but actually data preparation is not easy. So we need some tools to help us increase the data size and improve the quality. Crowdsourcing can help us easily reach a large number of workers for preparing data. It has played a key role in some applications. For example, the ImageNet dataset is prepared by crowdsourcing, and the ImageNet dataset has played the key role actually in the convolutional neural networks for image classification. And various crowdsourcing platforms have been developed, so including Amazon Mechanical Turk, PyBosa. I used crowdsourcing platforms for multiple projects, so they can help you to collect a large dataset much quickly than manual labeling or manual curation. So, but there are also some caveats. For example, you have to define the task clearly and consistently. Otherwise, when you are merging the results from multiple workers, you'll get into troubles. Secondly, the workers from different backgrounds may have different quality in terms of this work. So you have to be careful. So otherwise, you will introduce noise in the dataset. Lastly, so if your dataset is large, for example, if you put a large image dataset or text dataset onto Amazon for labeling, so there will be a high cost, especially if you use multiple workers for each to label or to process each example. The researchers working on crowdsourcing have started and proposed solutions to resolve these issues. For example, for quality control, for cost control, and the latency control. So please refer to the survey paper and the tutorial for the details. Many machine learning models are supervised learning models, so they require labeled data. The traditional approach is crowdsourcing. There are also some automatic approaches for labeling data, because crowdsourcing still requires human intervention. So it could be labor intensive. We want some tools or systems to automate this process. Weak supervision is one popular solution due to the development and open source of Snorkel. Developers define some weak labels. Here, the developers will define some weak labeling functions. So these labeling functions could use simple rules or some other machine learning models or just crowdsourcing workers. To give you one example of the rules in the labeling function, suppose we want to find the names of a couple in a sentence. So what we can do is to check if this sentence has words like marry, marriage, this kind of keywords. If there is, then the persons in this sentence will be labeled as a couple. So this is one simple rule. Yeah. So you can also use the labels generated by the crowdsourcing workers as the labeling function. So because the crowdsourcing workers may generate noisy labels, then you need to aggregate or to merge this results from the weak labeling functions. So that's what the snorkel is doing. So it will integrate the results and give each sample a label and also a confidence score. Since this label and confidence score can be further fed into the training model. Since the weak labeling functions are created in a cheap manner, so you just define the function instead of do the real labeling. So the whole process does not require intensive labor. Another way to increase the dataset size is to do data augmentation. It is an easy and cheap solution for increasing data size. The idea is to apply class-preserving transformations to the original data samples and to create new samples. For example, for the images, we can rotate the image, we can change the brightness of the image, we can crop the images to create new images. As long as we control the augmentation with the transformation degree, the content that will be visually similar to the original images. So we can preserve the class, but for the machine learning models, you will see a different input. Different augmentation methods have been proposed for text and images. So, and they are widely used in the applications. Actually, graph data is also a popular data modality, but graph augmentation is underexplored. We did one work on graph augmentation last year. To transform a graph, we can follow the image transformation to change every node attribute or to change every edge in the graph. However, if we do in that way, the class label could be easily changed because the changes to the nodes will be propagated and exaggerated. As a result, after the propagation, the content or the representation of a node will change significantly. And as a result, its label will be changed. So we cannot preserve the label. So in our work, we proposed to do augmentation for one single node at each time. So as shown in this figure, here we have 3 nodes. In the first iteration, we pick node 1 and do augmentation for node 1. Actually, when we do the augmentation, we will change the neighborhood of this node. So we can change the node attributes of its neighbor or change the edge connection of its neighbor. So we can also change the node itself. So then we will do the graph convolution and then make predictions. So in this way, for node 1, it will not affect other nodes, and for other nodes, it will has a limited influence on node 1. So we can preserve the class label. In the next iteration, we will pick node 2 and then change, do the transformation of the nodes and edges in its neighborhood, and then do the prediction. In addition, we add a consistency loss in the loss function, so which will minimize the difference between 2 predictions for the same node to preserve the class. For example, here, one prediction is from the augmented graph, and another prediction is from the original graph. So the consistency will try to minimize the difference of the two predictions to preserve the label. And this one is the original training loss using the supervised, for example, cross-entropy loss function. To improve the data quality is just to reduce the errors in the data. There are 5 common errors as listed here. Eliminating the errors may improve the model performance. Sometimes the improvement could be insignificant. It depends on the model, on the type of error, and the degree of the error. In the Clean ML paper, the authors evaluated these 5 types of errors for 7 traditional machine learning models. They found that by fixing the missing values and the mislabels, the performance is likely to improve, but the effect of inconsistency and outliers are not significant. If we remove the duplicates, so the performance may even decrease. For deep learning models, they have been shown to be robust to small errors. But if the error is significant, the performance would deteriorate. So for example, I know one case in production where the labels were wrong for a few days. First, it's very difficult to detect such kind of errors. Second, even you detect this kind of errors by observing the performance of the model, it's still very difficult to debug the error. So to handle these issues, we need to validate the data and detect the error, and then clean the data. TensorFlow X has the data validation function based on the data statistics, and the database community has proposed different data cleaning techniques, but they mainly focus on tabular data, so like the data in the database. Please refer to the listed papers for the details. Next, I'm going to talk about the model construction. For traditional machine learning models, the architecture is typically fixed. Given an application, what you need to do is to select one of the models and then tune the parameters of the model. But for neural network models, the architectures could vary a lot. Designing the neural architecture is sometimes referred to as alchemy. So recently with the development of neural architecture search algorithms, this step has been simplified a lot. So NAS only requires the developer to define the search space by configuring the layer set and the number of layers for the model. Then the search algorithm samples from the search space by connecting the layers and determining the type of each layer. The model is then trained and evaluated. The performance is feedback to the search algorithm for sampling new models. So after many iterations, we just need to output the model with the best evaluation performance. We applied NAS for a fintech application. We extended this AutoML0 framework to discover novel alphas. Alpha is a stock prediction model consisting of math operations over stock signals. For example, you can input the historical stock price into the alpha, which will predict the stock price for the future. Traditionally, alphas are proposed or designed by the fintech or financial experts. In Alpha Evolve, we search for the math operations for these 3 functions: setup, predict, and update. Initially, we generate many alphas randomly by sampling the operations for these 3 functions. And then for each alpha, we evaluate its performance. So it's like the training of our machine learning model. We call the setup function first, and then call the predict and update function by feeding the training data. And then we call the predict function to compute the loss or to evaluate the performance using the validation data. Then we will know the performance of this alpha. And we compare different alphas, and then based on the results, we can filter some alphas with no performance. And for other alphas, we can do mutation using the evolution algorithms. And then we will get new alphas, and these new alphas will be evaluated again to generate new alphas. So this process again will repeat many iterations until convergence. And then we output the alpha with the best performance. I'm not going to discuss much about the techniques for model training as they are well adopted in practice. So here I will just introduce one work we did for model debugging. So when implementing a new model, you may introduce bugs like in programming. So for example, here the operation should be addition, but you used subtraction. So this kind of errors are very difficult to detect because it will not lead to any runtime error or compilation errors. And even you know there is an error, it's very difficult to debug because the parameters W here is changing continuously. So given the same input X, so because W is different, the output Y is different. So it's very hard to control. So then it's very difficult to debug. And if you have the ground truth, you can compare the output of the model with respect to the ground truth. But for machine learning, sometimes you don't have the ground truth. So you don't have any reference for debugging. We worked on the graph convolutional neural networks to debug the implementation of graph convolutional neural networks. Here we used the metamorphic testing framework. The metamorphic testing guarantees that when we change the data, not the model, just the data, if the new data and the original data satisfy the metamorphic relationship, then the output should be the same if the implementation is correct. We proposed and they proved multiple metamorphic relations for graph convolutional neural networks. First, for example, the MR1 says that if we scale the attributes of any nodes in the graph by non-zero factors, the output is the same. And the MR4 says if we add or remove the edges outside of the receptive field of a node, the output is the same. This is because, for example, when we are predicting for this node, the changes of these nodes, they are outside of the receptive field of this node. So then the effect will not be propagated to this node. So this node's representation will not be changed. As a result, the output should be the same. So, but in your implementation, if you find that there's a change in your output, you will know that there will be some error in your implementation. To deploy a model, there are two scenarios. We can deploy the model on a server or on the edge devices. So when we deploy a model on a server, we can do batch processing to improve the throughput. But it will increase the latency because to create a batch, you have to wait for more requests. We can also do ensemble modeling. For example, I have 3 GPUs. I can use these 3 GPUs to run 3 different models to process the same request. And then the results will be aggregated to improve the accuracy. But it will hurt the throughput because we can, instead we can run 3 GPUs for using the same model to process different requests. In this way, the throughput could be higher. Yes, we need to treat the trade-off. We need to balance. When you deploy the models on edge devices, you may need to do some compression to reduce the computational cost to save the battery. And there are other techniques that should be considered, like interpretation for model serving. Again, I will not go into the details. You can please refer to these papers for our works on these directions and also the related works from other authors. Last, I will talk about the job management and the pipeline management. We started one problem in job management, that is training job scheduling. So here I have 3 jobs, and I have 2 GPU servers. On each server, I have 2 GPUs. So this figure shows one schedule for the jobs to the GPUs. So I will run 2 GPUs for the job 1. This means the batch size of this job will be larger. And I will run 1 GPU for job 2 and another GPU for job 3. Yeah, so in our algorithm, we'll convert this schedule into a vector encoding. Then we use evolution algorithm to find the optimal schedule to minimize the average job completion time. So we will start with random assignments. So we'll be generate many random assignments. And then we will generate new schedules by evolution operations. For example, to change the initial population, initial assignments. And then we will reorder the schedules based on a remaining utilization function we proposed. So this utilization function will consider the estimated remaining training time and the number of GPUs, which will decide the batch size of the model. And again, which will in turn affect the remaining time. So we will filter out no score schedules and continue the jobs using the schedule with the highest scores. So yeah, in this way, we will repeat step 2 and 3 periodically to change the schedule of the jobs. In terms of pipeline management, I use one example from Google and using Berkeley. So this is a pipeline of a single model. We can see there are different operators involved in this pipeline. If we deploy this model for online production, the pipeline becomes like this. So it's very complicated. This is because the model may have multiple versions, and we'll have to keep updating the model with new data. So the pipeline is like this. For such a complex pipeline task, so we need a platform to manage it. Otherwise, manually launching each operation in the pipeline is tedious and error-prone. So this looks like an engineering task, but actually there are some research opportunities. For example, the authors found that there are some pipelines that will be killed, that will fail before the ending. So if we can have a model or some ways to predict such cases, we can stop this kind of pipelines early to save the computational cost. Another example is that they found that some intermediate results are reused by different pipelines. So if we did find such kind of results and do materialization for them, we can also save the cost. Yeah, so that's all the algorithms I want to introduce. Next, here is incomplete feature comparison of the existing platforms towards an easy to use AI, to make AI easy to use. So this comparison is just based on my limited personal knowledge. So it's not a comprehensive. Different systems or platforms have different focus. For example, Auto SK9 is based on SK9, which has included the traditional machine learning models. So this tool will do the model selection and hyperparameter tuning automatically for you. And AutoKeras is based on Keras for deep learning models. It will do neural architecture search. And the NNI is good at hyperparameter tuning. And TensorFlow X has the data validation functions. SingAeasy is one platform we are doing at National University of Singapore. So we have some novel techniques in the model serving stage by trading off the batching and ensemble modeling. Kubeflow is based on Kubernetes. So it's very general. Any tools, you can deploy any tools on Kubernetes. So you can also integrate your tools into Kubeflow. ML Flow is good at model tracking and deployment. Or yeah, SageMaker, Google ML, Azure ML, and other cloud platforms. They provide support for each stage of the machine learning lifecycle. So they have simplified the development of AI applications significantly. Okay, that's all for the presentation. Here's a summary. I started with the discussion of the adoption of AI and machine learning in various domains. So we found that for some traditional domains, AI and machine learning have been massively adopted. But for some new domains, the adoption is actually a bit slow. So I think there are at least two challenges. So I reviewed the algorithms for the second challenge towards easy to use AI platform from the data preparation, model construction, training serving, pipeline and job management perspectives. Finally, I briefly introduced compared some platforms in terms of the features to support, to make AI easy to use. Okay, so that's all. Thank you, Sam. Thank you for listening.
Thank you, Wang, for the interesting talk. I would like to go over into a short Q&A. We have a couple questions for you. First one would be, among all these introduced techniques for making AI easy to use, which one or two are the most important ones in your mind and why?
Okay, based on my personal experience, I think data labeling and the automation of the pipeline are the most important. I worked on both image and the text tasks. For example, we developed an image labeling website at NUS to label Singapore food images. The workers, the students in the research lab, it took us about 2 months to label and clean a food image dataset with about 200,000 images. Yeah, so it's quite slow, the process. We also used Amazon to label a text dataset consisting of news articles. First, it's not cheap. If you ask multiple workers to work on each single article. Second, we got issues in merging the results from different workers when there is no consensus. So, I mean, cross-sourcing is the killer for data labeling. So there are also some issues. We also tried Slowcurl, the tool I introduced, which was developed from Stanford. It helps, but the quality and the coverage depend on the user provided weak labeling functions. So still involves some user intervention. In terms of the pipeline, I think it is also important, but there are some solutions I think work towards this problem, because there are many models and tasks in a company, for example, in ByteDance. So these models need updating frequently and continuously. Manual operation is almost impossible. So how to automate this process efficiently and effectively is the challenge.
Next question, and to the audience, I mean, if you have more questions, please put them in the Rocket chat box so I can pass them on to Wei Yang. I do have one more question here. Is there a single tool that integrates all the mentioned techniques? What are the challenges of integrating them together?
So far, I haven't seen a single tool or an open source project that provides all these functionalities or features. But there are such kind of toolkits, for example, the Kubeflow and the cloud platforms like Amazon and Google. So they integrate, they have different subsystems, but they provide this kind of service, these services together on the cloud platform. I think there should be some startup companies working on this direction. At least the so-called AutoML companies, they provide some services. For example, for the training, the hyperparameter tuning, and the model deployment. Some may also have the data preprocessing, for example, data labeling. features. I think there are a few challenges. The first one would be the engineering effort. So it requires a lot of effort to integrate these different multiple complex tools together. So these systems usually they have different inputs and output formats. For example, the labeling part, the training, and the inference, they may have different data formats. So the data cannot flow smoothly from one system to another system. So some stages in this pipeline may require intensive human involvement. So we may need to do for example, the labeling, do the configuration setup manually, and then collect the results, merge the results, and then clean the data, and then continue with the rest training and or inference part. So I mean, it's like ad hoc tasks. So from this perspective, I think maybe the motivation is not very strong. So people just handle them individually and separately. So they just install these tools one by one in a cluster to share the infrastructure. So for example, the file systems and the computing resources. They just do it manually. So they may, of course, if there is such kind of integrated platform provides all these kind of services, it would be more convenient for the users. But so far, I think the users can still work around it. Yeah. So yeah. So I think that's the situation.
Okay. Thank you very much. I haven't received any other questions from the audience, so I think with that, I would like to end our discussion. Thank you again very much for being here.
Thank you, Jackie.
And yeah, wish you a great rest of your conference. Thank you very much, everyone. Bye-bye.